She was found with cut marks on her bones that appeared as though her remains had been cannibalized. This does perhaps imply an act of desperation.
That act of desperation would have happened in Jamestown, Virginia, during the Starving Time, a period over the winter of 1609 to 1610, when drought, hostile relations with nearby Native Americans, and a lost supply ship wiped out most of the colony. Some writings from that time allude to cannibalism among the colonists, but there had never been physical evidence that it had occurred. That is, until 2012, when archaeologists uncovered the remains of a 14-year-old girl who had come to be known as Jane, and whose bones told a grisly story.
It does appear that she was butchered in some way.
That's Christine France, a research scientist at the Smithsonian's Museum Conservation Institute in Suitland, Maryland. France is a specialist in stable isotope ratio analysis and was called in to help analyze Jane's bones. Armed with mass spectrometers and a bone saw, Christine probes archaeological remains for chemical details about how individuals lived and where they spent their time. Although anthropologists have many clues about what may have driven the Jamestown colonists to butcher one of their own, they don't know much about Jane herself. And that's where Christine comes in. Understanding who Jane was could help them better understand this formative time in American history.
It's really the origin of our country. Understanding who these people were, why they came here. Was she a servant? Was she upper class? Was she middle class? What might have driven this young girl? She was only about 14 years old. Was she brought by her parents? What motivated them to come here and do this? I think that's something that a lot of people want to be able to understand.
You're listening to Stereochemistry, and I'm your host, Carrie Jansen. In this episode, we're going to delve into this and two other cases in which anthropologists seeking to fill in historical gaps turn to isotope chemistry for answers. The stories involve not only starving Jamestown colonists, but also the transatlantic slave trade and 18th century pirates. What ties these tales together is bones, a search for identity, and Christine's isotope lab. Christine shares her isotope insight with other researchers at the expansive Smithsonian Institution and at archaeological sites throughout the world. She also sometimes works with law enforcement agencies investigating contemporary cases of unidentified remains. Stereochemistry visited Christine's labs in Maryland to see the tools she uses to uncover the stories hidden in bones. That journey begins in a small room where drawers painted a cheerful baby blue are stuffed to the brim with bones and teeth.
We have hundreds and hundreds and hundreds of samples. These are all the North American remains.
The chemical composition of our bones reflects choices we make throughout our lives. Encoded in these chunks of collagen and mineral material is information about our lifestyle and where we spend our time, in the form of stable isotopes. In her work at the Smithsonian, Christine is primarily interested in the isotopes of carbon, nitrogen, and oxygen, elements that are plentiful in the human body. Each of these elements comes in a couple of stable isotope flavors. Carbon, for example, can appear as carbon-12, the standard, most abundant flavor of carbon, or carbon-13, which has one extra neutron. By looking at the ratios of these elements in bones and teeth, Christine can learn things about their source. For instance, measuring those carbon isotopes can help her understand the types of foods a person ate. Staple crops, like corn and wheat, fall primarily into two groups, called C4 and C3 plants, named for the 4-carbon or 3-carbon intermediate molecules that are produced as the plants perform photosynthesis. Those two types of plants process carbon from the atmosphere differently, and that signature is retained when our bodies use that carbon to build our bones and teeth.
Back in grade school, you're taught that photosynthesis is the process where a plant takes sunlight and carbon dioxide and some water and creates food for itself. And you're taught that photosynthesis is photosynthesis. Well, that's not exactly true.
C4 plants, like corn, end up with slightly more of the rare carbon-13 isotope in their tissues than what you see in C3 plants like wheat. And by measuring the abundance of those isotopes in bones and teeth, Christine can tell which of those two types of plants make up most of a person's diet. The bones of a corn-eating North American will look different in the mass spec than the bones of a wheat-eating European. And just to be clear, Christine isn't putting entire bones into the instruments. She collects about 200 milligrams from samples using such sophisticated laboratory equipment as a Dremel rotary tool.
I just bought this from Home Depot.
Christine said Jane's carbon isotopes suggested a wheat-based diet, which is what you would expect in a recent European immigrant. No surprises there. This was early 17th century Jamestown after all. But there was more to the colonists' diet than just plants. And so to learn more, Christine also looked at Jane's nitrogen isotopes, which are influenced by the amount of animal protein a person consumes. People who eat a lot of animal protein accumulate more of the heavier nitrogen isotope, nitrogen-15, in their bones. In the early 17th century, around the time of Jane's death in Jamestown, the amount of protein a person was eating would likely have been closely tied with her social class. Wealthier people had access to more meat. Anthropologists believed Jane, as one of the few female residents of Jamestown at the time, would have been the daughter of a gentleman, or possibly a maidservant to a high-status family in Jamestown. Perhaps her diet, documented in her bones, could offer confirmation. Here's Christine.
So unfortunately, the nitrogen was not as informative as we had hoped it would be. We didn't see anything that suggested she was eating a lot of proteins, suggesting that she may have been upper class, having access to resources that others didn't. We didn't see anything suggesting that she had no protein in her diet, suggesting perhaps that she was lower class. We didn't see either of those two extremes, which would have maybe pointed us in one direction or another.
So Jane's diet was not distinctive enough to reveal her role in Jamestown society, but researchers hoped they might be able to find out more about her by scouring historical documents like ship manifests for someone matching her description. They knew from her carbon isotopes that she had recently arrived from Europe, and they hoped Christine might be able to help them focus in on a particular region where Jane's journey had started. For that information, Christine looked to the oxygen isotopes. Most of the oxygen in our bones and teeth comes from the water that we drink, and the oxygen isotopes in that water are influenced by climate and the way air circulates around the planet. High temperatures near the equator cause a lot of water to evaporate into the atmosphere, and as that water migrates to higher latitudes, some of it begins to condense and fall as rain. Water made of the heavier oxygen isotope, oxygen-18, condenses more readily, while water made of the lighter oxygen-16 tends to stay in the atmosphere. So as atmospheric water moves toward the poles, it's gradually depleted of the heavier oxygen-18.
So as you move away from the equator, the ratio of the heavy to the light isotope changes in a pretty systematic and pretty noticeable way. Several hundred, several thousand years ago, people didn't move around quite as much as they do today. They were a little more local, drinking more localized water. You can then look at the oxygen isotopes in the bone, so we can then sort of back calculate and roughly place a person on a map.
Christine compares the results from a sample to a database of water data from all over the world to produce a map of an individual's likely origin. Now, this map doesn't come with a big arrow pointing exactly to where an individual was born, but it can show which areas are more likely than others. In Jane's case, Christine found the girl likely grew up in the southwest of England, possibly in a coastal location. That information may help researchers narrow down their search as they probe historical records for any mention of a young girl about 14 years old who traveled to Jamestown in the early 17th century. But of course, there are limits to what isotope analysis can tell you by itself. It can't tell you how Jane died, or her real name, who her family was, or why she came to Jamestown. You might wonder why it's worth subjecting these precious samples to Christine's bone saw or rotary tool. We spoke with a forensic anthropologist and curator at the Smithsonian's National Museum of Natural History, Doug Owsley, to learn why his team called on Christine.
This is all about our history and where we came from and the people that preceded us. These are such important archaeological sites in terms of our American history. When you're talking about Jamestown, for instance, I mean, these are the people that founded who we are today. This is the whole kernel of our American way of life. When you look at American history and what is recorded, it is going to focus, of course, on people of European ancestry and usually males, almost always. Women are going to, in the 17th century, for instance, live completely in the shadow of their husbands many times. Children come and go, and nobody writes a single word about them. And so all of these are different pieces of information that are like a giant jigsaw puzzle that we tie together to tell the story of a person for which nobody ever wrote a word about them that survived to us today.
So that's where we'll leave Jane. But that motivation takes us to another set of remains that might help us understand the stories of individuals often overlooked in historical records. In this case, enslaved Africans. Doug and Christine have examined remains recovered in Elmina, a city on the coast of present-day Ghana that was once a major port in the transatlantic slave trade. Christine told us she runs about 10,000 analyses in a year, and that she feels particularly fortunate to be working with the Elmina remains.
It's just a really unique set of remains. It is one of the better preserved archaeological sites in Africa. That's why it's important. We have some good historic documentation for it, so we know a lot about it. And understanding that history helps us put these remains into context.
The hope is that by analyzing remains found in Africa, anthropologists might be able to establish a baseline of isotope levels to which they could compare isotope levels in the remains of enslaved or free Africans and African Americans buried in North America. This might help us better understand the behaviors and experiences of individuals of African ancestry during the time of slavery.
I'm hoping that maybe we can breathe some life back into these individuals that we didn't know a whole lot about. I think that would be a good thing.
When Christine analyzed the carbon isotopes in the bones from Elmina, looking for indicators of the types of plants being consumed, she said she found some interesting clues about how diet preferences can cross an ocean.
I think the most interesting thing that came out of that The African population from Elmina relied heavily on C4 grains. Those are going to be things like millet. They didn't quite have the same kind of corn diet that we do here in North America, but millet is a very similar type of grain. When we look at African American populations, they reflect a similar food choice. So they also reflect these C4 grains. In North America, it's probably going to be more corn than millet, but they are definitely choosing that over the wheat-based grains. Even in northern areas, even if they're living in urban areas, they're still retaining some of that cultural food choice, which I thought was really interesting. That was one of those unexpected, wow, that's really neat kind of moments. We weren't looking for that, but it showed up in the data, and we thought, oh, that's kind of neat.
But Christine and Doug had another goal for the isotope analysis of remains from Elmina. Since oxygen isotopes can help clarify an individual's region of origin, they hope to use the bones from Africa as a sort of control population to help in their study of burials in North America. That would enable anthropologists to better understand whether remains of African ancestry found in North America belong to someone who lived there for a long time, who was perhaps born into a system of slavery, or someone who had arrived more recently from Africa. An important factor for anthropologists to consider as they work to understand an individual's experience.
What we're able to do then is to not speak in such general terms about what slavery meant for individuals, and we can look at how those different birth experiences may or may not have also played out over the course of the lives of these people.
That's Joe Jones, an anthropologist at the College of William and Mary, whose work involves using isotopes of strontium as well as oxygen to determine the origins of remains from the New York African burial ground.
We start to get a much finer picture of these people really as people as opposed to data points or nameless, faceless individuals. Particularly for African American and other African diaspora populations, often the documentary evidence can be skewed, often can be missing. And so this does become a really powerful, one source of evidence amongst others, but a really powerful one given the particular history of enslavement in which people's voices were either muted or sometimes distorted or left out altogether. So the skeletons can speak to some of these experiences where we don't have access to that other data. Sometimes it can be useful to do this skeletal analysis in order to confirm what we already know, but sometimes we get new evidence that can help expand or even challenge some of the stories that we think we know.
For example, understanding where an individual found in North America was born may be able to reveal whether the person was smuggled into North America after the transatlantic slave trade was outlawed, or reveal other information about the movements of a population. At the Smithsonian, Doug asked Christine to analyze the isotopic ratio of oxygen in the bones of about 40 sets of remains found in Elmina and compare them to oxygen isotopes from individuals born and raised in North America. But they weren't sure the African samples would be distinctive enough to be effective control samples.
The question was always, how much difference is there going to be in the oxygen isotopes between the African population and the North American population? Is there enough of a difference that we could even see it in the data? If you can't see a difference, then it's not going to be a very useful tool to determine which individuals from North America recently arrived from Africa. As it turns out, we think we can see a pretty solid difference. We think that if we were looking at a population from kind of the middle Chesapeake area, and we saw one of these outliers where the data kind of looks to be different from the rest, we could compare it with that African population and say, yes, that does look like someone who probably recently arrived from Africa and was not necessarily born into this system of slavery. So that was pretty exciting.
Work is ongoing to better understand the lives of enslaved individuals buried in New York and throughout the Chesapeake region. Here's Joe Jones again.
There's the scientific curiosity factor, of course, but at the same time, we understand the desire and the need for people to have those connections, those historical and cultural connections, and we really see this science as a part of that process, helping people reconnect some of the dots of history that have been broken.
When we come back, we look at what the isotopes can tell us about a man who may have a pirate connection.
Hey everyone, Doria Reiser here. I'm CNEN's Audience Engagement Editor, and I'm here to tell you about a great way to stay up to date with the chemistry news you need to know. It's our newsletter. Every week in your inbox, you'll get not only the latest news, but also some really cool extra content, such as periodic graphics, which are in collaboration with Compound Interest, or Chemistry and Pictures, which features submissions from you guys. Sometimes we even set up special features, such as what's going on in policy or in the environmental realm. You can sign up for our newsletter by opening your web browser and typing bit.ly/chemnewsletter. Just point us to your inbox and we'll take it from there. Again, that link is bit.ly/chemnewsletter. We'll also include that link in this episode's description. Now back to the show.
Looking Glass Productions.
Hi, is this Kevin Duffus, the Blackbeard historian?
Yes, it is.
My name is Carrie Jansen. I'm a reporter at Chemical... I promised you a story about pirates, and here we are. Our final case of the episode comes from North Carolina, where in 1985 a set of remains was discovered near the port city of Bath. The bones were presumed to belong to one Edward Salter, who had owned the land at the time of his death in 1735. Eventually, the bones made their way to the Smithsonian's Doug Owsley, who was asked to examine the remains and try to determine if the unnamed bones were indeed those of the late Edward Salter. But there was another layer to this story, and that's what brought me to Kevin Duffus, a research historian in North Carolina who has written extensively about the 18th century pirate known as Blackbeard. In fact, he insists the infamous Blackbeard was actually a pretty decent guy, as far as pirates go. Whether or not you agree with all of his conclusions, Duffus is immersed in the history of Blackbeard and his associates, and I happen to find myself needing some information on that very subject. Strangely enough, a story that I'm working on has led me to Blackbeard.
Well, I don't know how much he knew about chemicals and engineering, but I'm interested to hear what the connection is.
Here's the deal. Blackbeard was an English pirate who operated from 1716 to 1718 along the eastern colonies and the West Indies from his ship the Queen Anne's Revenge. According to Duffus, on December 1717, Blackbeard pillaged a merchant sloop near Puerto Rico and took for his own crew 3 skilled laborers, one of them a cooper, a barrel maker.
They said, "What do you do?" And he said, "I'm a cooper. I build barrels." He goes, "Okay, from now on, you're with us."
The cooper's name was Edward Salter. When Doug examined the bones found in North Carolina, he observed physical markers that indicated the individual had engaged in strenuous use of his arms, like you might if you, say, made barrels for a living. So we have a set of bones found in North Carolina. We have a man named Edward Salter who owned the land where the bones were found, and we have Edward Salter, a pirate's barrel maker. Could they be one and the same? Kevin Duffus is a believer. He said his research indicates Salter left Blackbeard's crew before the infamous pirate's death in 1718, and that Salter was able to evade hanging, the typical punishment for a pirate, thanks to a royal pardon. He believes this Edward Salter settled in North Carolina, in Bath, where historical records refer to a man by the name of Edward Salter buying and selling property just a few years later.
The fact is that Edward Salter was a barrel maker, and barrel makers could find work anywhere. I believe he met a woman and fell in love and married her and eventually produced a rather sizable family.
And if that is indeed what happened, it's that sizable family that could prove the key to completing Edward Salter's story. If genetic information from the bones could be linked to living descendants of Edward Salter, that would confirm the remains' identity. And historical family documents could reveal even more information about the man who may or may not have spent time aboard Blackbeard's ship. But the challenge is defining Edward Salter's family tree. Genealogists working on this project found not one, but several Salter families with roots in early 18th century colonies. To help narrow down the search, Doug once again called in Christine and her mass spectrometers.
The genealogists were having a heck of a time. So they came to me partially because they wanted to know if I could give them a region of origin to sort of help them pinpoint which family tree they should look at a little more closely. But the other factor of this was we're trying to figure out, could this individual have actually been one of Blackbeard's pirates? The only way to figure that one out is probably to find some historical documents. Well, you're not going to find historical documents unless you can dig back into the family lineage and get into the family documents and see if there's any evidence there. It's like a Venn diagram of trying to relate all of these different things together. But first we got to find the family lineage.
Isotopes can't tell you if someone lived on board a pirate ship for just a few months, but Christine was able to determine from oxygen in the bones, which, remember, comes from latitude-specific drinking water, that the man buried on Edward Salter's land was likely from the North Carolina, Virginia area.
We're looking at kind of the southeastern United States, but not deep south. You know, there were some lineages from up in the New England area, but now the genealogists know that that's probably not going to be him. They're going to focus more on some of the lineages that they have found in the historic records that suggest that kind of southeastern United States area. So now they sort of have a target. Isotopes cannot tell you which lineage you're from, but they can help you get into the right historic documents to try to figure some of that out.
So did this crack team of genealogists figure it out? Do the bones belong to Edward Salter, the North Carolinian landowner and possible former pirate?
We don't know yet. They're still working on it. Yeah, that's an in-progress project, I'm afraid.
Our goal is really to tie this all together in terms of basically the story of the Chesapeake as being a story told in bones. That's the real treasure, is what the bones can tell us about this time period.
That's Doug Owsley again, talking about the motivation for his work and how analytical chemistry fits into that mission.
You know, the isotope chemistry is such an important part of that. we're able to carry these studies further than I, in my lifetime, would have ever imagined. And I'm fully aware that the next generation will be able to go further. So the techniques that are coming online, the different types of isotopes that Christine is doing research on, that's going to carry us to another level of investigation. And I think that it's just truly amazing, extremely challenging, but also very exciting.
As you might imagine, carbon, nitrogen, and oxygen aren't the only stable isotopes that appear in archaeological remains. So what else is out there? Well, remember, there are researchers like Joe Jones who study strontium, and other elements, such as hydrogen and sulfur, could also form the basis of future research. Here's Christine.
The sulfur is going to be, I think, our next big frontier. Sulfur is very poorly understood in vertebrate tissues and bones and teeth. I want to start looking at it, and I want to compare it to the nitrogen to see if it reflects diet. I want to compare it to the oxygen to see if it reflects any kind of region. I'd love to compare it to strontium.
And while chemists like Christine study and develop these new techniques, they also have to accept the limitations to what they can do now. That despite the power of modern chemistry to look back into the lives of real people from hundreds of years ago, some details remain out of reach. We asked Christine if that ever frustrates her.
Always. I want to be able to put my samples on my instrument and get every answer that I ever wanted. It would be like magic, but it's never like that. Science is never like that. Before I was actually working on a lot of human remains, I worked on Pleistocene mammals. When you're working with mammoths and mastodons, they don't really have a personal history. So, you can learn interesting things about them, but it's not quite the same as working with a pirate or a cannibalized young woman. I enjoy it, and it frustrates me because we'll never know the whole story. I'll find as much information as I can, but more often than not, we don't always get closure. But that's okay. That just means there's more science to do.
Next month on Stereochemistry, CNN reporter Lisa Jarvis explores how drug hunters are targeting proteins long considered undruggable. If you haven't already subscribed to Stereochemistry, go do that. We're on iTunes, Google Play, and TuneIn. Thanks for listening.